Hello, welcome to this continuation of dot product. We talked about the basic way to compute a dot product. We talked about using it to find the angle between two vectors and following that formula. So this video will cover two applications of the dot product. The first one being projections of one vector onto another. We are going to start with some vectors in 2 dimensions, but keep in mind we can also do this in 3 dimensions. So we'll come back to vectors A and B. I want to just go over this notation first. When you see this first notation, if I were to read this, it would say the projection of vector A onto vector B, which seems a little out of order, but we use the subscript B to show the vector we are projecting onto. So we are projecting A onto B. The second one here, we use this ORTH. Now, again, discussing the angle between vectors. If we are talking the angle between two vectors, we sometimes will look for orthogonality, just another word for perpendicular. So this right here would mean the orthogonal of the projection of A onto B. So once we find the projection of A onto B, we are also sometimes asked to look for the orthogonal of that projection. So we are looking for a vector that makes a right angle with our projection. So let's go ahead and we'll do a little math here. You know, it's always good to do a little math. So we are going to graph A and B. So A, 1, 2, 3, 1, 2, 3, 4, 5. Looks like this. And we are projecting that onto B, which is noticeably smaller over here at 1, 1. So when that happens, yes, we are projecting A onto B. The idea is that even though B is this tiny vector, if I were to extend it out further, it would act as a floor. When I'm projecting onto something, it doesn't matter in the sense that B is diagonal. It's acting as a floor. And if I'm doing something like shining a flashlight above A. So let me see how my drawing skills are. So here's my flashlight. And that flashlight is shining light. This light is orange, by the way. I guess I could change it, but hopefully you get the idea. So I'm projecting a light directly down towards that floor of B, okay? My projection will be a new vector that creates that perfect shadow of A onto B. So that's the idea. It's like creating a shadow if this is my light, okay? The orthogonal to that will be essentially where that shadow cuts off, and that would be at a right angle like that. So let me label these real quick. This pink one is my projection vector of A onto B. This purple over here, making the right angle to that where my shadow cuts off, would be the orthogonal of A onto B. Okay, so that's kind of what this looks like. So then how do we figure out what that is? Well, there's a little bit of a formula, and just as a fun fact, and you're going to see it here. Let me give you the formula to find the projection. Finding the projection of A onto B, then what I am doing is I am taking the dot product of A and B divided by the magnitude of B squared. And this is going to give me a scalar. When I do this portion in parentheses, I get a scalar. And I take that scalar and I multiply it by vector B, and hopefully that makes sense. This is going in the same direction as B. So I'm essentially applying a new magnitude to B, or I'm taking B and I'm stretching it however much further it needs to go to create this projection. So the interesting thing here, what I'll point out off to the side here, we have this magnitude of B squared. So, okay, I'd have to find the magnitude of B and then I have to square it. The interesting thing about this is actually the same thing as taking the dot product of B dot B. Okay, so let's test it out. The magnitude of B up here, the magnitude of B is going to be equal to the square root of 1 squared plus 1 squared. So it looks like I'm getting the square root of 2. Not very interesting, I know, because we have a bunch of 1s in there. All right, but if I take B dot B, remember we are taking 1, 1, and we are dotting it with itself. So I think what you're going to see is we are getting these pieces that are being squared, okay? So if I'm doing 1 times 1 here, I'm getting 1 squared, and remember then we add the other 1 times 1 squared. Or I'm sorry, just 1 times 1, which is 1 squared, okay? So again, I get 2 for this, but keep in mind that this magnitude of B squared is going to be equal to just 2, which is our dot product there. So you might see this written either way. Let me see if I can undo that. That's my bad. Okay. So you might see it written as the magnitude of B squared. You might see it as B dot B. Either way, same thing. You can decide how you want to memorize that. So if I do that, if I take this little formula inside of the parentheses part, I am going to get 8 over 2, and then I'm going to use that as a scalar multiple multiplied by B, which is 1, 1. So essentially my projection here would be the new vector 4, 4, which if I look at my drawing makes sense. Okay, if I would have drawn it maybe a little bit more to scale, that would have been up a little further, but you know, not perfect here. What can we do? So this is my projection, but keep in mind, we also want to find the orthogonal of the projection. That part is super easy, but there is a check that we want to do for that. So it's super easy because essentially what we're doing to find the orthogonal is we're going to take A and we're going to subtract what we got for our projection. Okay, so taking A, subtracting out the projection leaves us with the orthogonal. So that means we are taking 3, 5 minus 4, 4, and we are getting an orthogonal. I did that backwards. Orthogonal of A onto B is going to be negative 1, 1. Okay, and we can look at that. We got this negative in here. Well, think about, you know, if I am starting from an initial point right out here at 4, 4, and I go back 1 and I go up 1, that gets me onto that tail of A. All right. Now, this is the reason why we have to check here is this is assuming that we did that projection correctly. And you know what? Hey, we're all pretty good at math around here, but it doesn't hurt to check, okay? The way we check is the same way we check anything for orthogonality. We're looking to see if the dot product equals 0. So if this is truly the orthogonal vector that we found here with negative 1, 1, then it would be true that if I take B and I dot it with that orthogonal, that I should get 0 if they were truly perpendicular. All right, so we'll give it a try. B is 1, 1. Our orthogonal is -1, 1. It is looking good because that looks like that's going to be -1 plus 1. Oops, I skipped ahead of myself because I got so excited. -1 plus 1, which does equal 0. Okay, so just a quick check you can do to make sure you did both of those right. All right, now this next one I don't have an example for. I'm just going to walk you through really quick because we don't talk about direction cosines very often, but this is the way to get around the whole direction angle thing when you're in 3 dimensions. In 2D, whenever we're talking direction angle, it is always based off of the positive x-axis. Well, when we are in 3 dimensions, we have a lot of different directions we can go. And so we use alpha, beta, and delta to represent 3 different direction angles, okay? Those direction angles or the direction cosines will use the idea of a dot product with the unit vector in whichever direction you're headed. So this v dot I is referring here to my unit vector in the positive x direction, which we call I. So if I'm trying to find the direction angle with that, that would be alpha right here. And now this is the part that it's kind of hard to tell, but there is a little bit of dimension here. It's coming from that positive x-axis out to your vector in space here, okay? So finding that angle there, that you would take the dot product of v and I, okay? And then you would apply this formula. So the cosine of alpha is equal to that v sub 1, okay, which is your dot product there. And you would divide out the magnitude of v. Okay, so that is similar to finding the angle between 2 vectors in 2D. That's essentially what you're doing here. It's very similar to finding the direction, or I'm sorry, the angle between 2 vectors, okay? Because that's essentially what we're doing. So you can do that for any of these directions where J would then represent your positive y-axis, K would represent your positive z-axis. And to kind of describe all together, you know, what that would look like, you can check. I mean, if you're checking these direction cosines, the cosine squared of alpha plus cosine squared of beta plus cosine squared of delta should equal 1. And part of that has to do with the idea that you're kind of dividing out your magnitudes here and you're using all of your unit vectors essentially. So that's just kind of a quick overview. It's in the homework. It is hopefully pretty straightforward. Let me know if you have questions, but just know that that's not something that we actually spend a lot of time using. It's just an application that it may come up here or there, okay? If it does, and this is something that, you know, you can ask me about quite frequently throughout our class, and you'll probably hear me say, there are some formulas you do have to memorize. This would not be one of them. If you were asked to use this, it would be on a formula sheet for you. So just FYI that is the situation. So hopefully this helps. Let me know if you have questions, and hopefully I'll talk to you soon.